Far beyond the Sun, past the orbits of Jupiter, Saturn, Uranus and Neptune, lies a distant region that few people truly understand. This is the outer edge of our solar system, a vast area where sunlight is extremely weak and temperatures are lower than anywhere on Earth. This region contains objects that have existed since the solar system first formed: frozen worlds, drifting comets, and boundaries that show where the Sun's influence ends and interstellar space begins. Astronomers refer to this area as the Kuiper Belt, and beyond it lies the Oort Cloud, a spherical region of icy material that may extend halfway to the nearest star. Before we begin tonight's journey, comment below where in the world you're watching from and what the time is there now. We're always excited about hearing where our viewers are from. When we look deep into space with our most powerful telescopes, we can see galaxies that lie billions of light years away. These glowing islands of stars show us what the universe looked like long ago, even allowing scientists to estimate what it may have been like shortly after the Big Bang, the immense explosion that began everything around 13.8 billion years ago. We can even measure how fast the universe is expanding, watching galaxies drift farther and farther apart. Yet, no matter how far we look, there is always a mysterious limit, an invisible boundary beyond which our eyes, even with the best technology, cannot see. But what does that really mean? What might exist past this unseen horizon? Could the universe continue forever, stretching endlessly without an edge? Could it perhaps loop around itself like a great cosmic circle? Or are we living inside a vast bubble with boundaries we can never cross? For anyone who has ever looked up at the stars and wondered, how far does it all go? This is a question that sits at the very heart of our curiosity. Where does the universe end? And what does end even mean in a place as vast as this? When we imagine space, it is natural to think of it like a giant bubble, something with a clear edge, the same way a balloon, a country, or even a map seems to have limits. But when scientists talk about the universe, things are far more complex. In fact, asking where the universe ends might not even be the right kind of question. That's because space itself doesn't seem to have an edge at all. To understand why, we must first think about what space actually is. In our everyday world, everything has a border. A field has a fence, a city has limits, a house has walls. But the universe isn't a thing sitting inside something else. It is space itself. So when we ask where it ends, it's a bit like asking what's north of the North Pole. The question doesn't really make sense once we understand the shape of what we're talking about. One idea many scientists believe is that the universe might go on forever. This concept is known as an infinite universe. If the universe truly is infinite, then there is no edge, not even a very distant one. No matter how far you travel in any direction, there will always be more space ahead of you. You would never hit a wall or a border because there simply isn't one. The universe would be boundless, continuing endlessly. Of course, this is difficult for most people to imagine because in our daily lives we never deal with infinity. Everything we know has a beginning and an end, but mathematically, infinity makes sense. If space doesn't curve or fold back on itself, then it just continues forever. However, there is another possibility. The universe could be shaped in such a way that, if you kept travelling in one direction long enough, you might eventually end up back where you started, just as a person walking straight east on Earth would eventually circle the globe and return to their starting point. Earth feels flat to us when we walk on it, yet it is round, and that curve is only noticeable when we see the planet from space. The universe might work in a similar way. If that's true, then space doesn't go on forever, but it also doesn't have an edge. Scientists call this kind of universe finite but unbounded. It means that the universe has a limited size, yet it curves back on itself so smoothly that you would never reach a wall or a stopping point. This idea fits well with Albert Einstein's theory of general relativity, which describes how space can bend and twist under the influence of gravity. According to Einstein, if the universe contains enough matter and energy, its shape could curve inward like the surface of a gigantic sphere. We might not see that curvature easily because space is unimaginably vast, but over enormous distances it could make a real difference. Both ideas, an infinite universe or a curved looping one, agree with what astronomers have observed so far. The difficulty lies in the fact that we can only see a limited part of the cosmos. Light travels at a fixed speed, and since the universe has existed for only about 13.8 billion years, we can only see light that has had enough time to reach us. The region we can observe is called the observable universe. You can imagine it like a glowing bubble around us, containing everything whose light has arrived here since the beginning of time, but that edge is not the true end of the universe, it's simply the farthest distance we can currently see. Because of this, we can't yet tell whether the universe truly goes on forever or loops back on itself. Both remain possible. What we do know is that galaxies continue in every direction as far as our most advanced telescopes can detect. The farther we look, the faster those galaxies seem to be moving away from us. This happens not because they are flying through space, but because space itself is expanding. Imagine small dots on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they are travelling across the surface, but because the surface itself is stretching. In much the same way, the galaxies are carried apart by the expanding fabric of space. In this picture, there is no real edge to the balloon surface. You could walk around it endlessly without finding a border. The same may be true for our universe. Some people wonder, if the universe doesn't end, then what lies outside it? But that question doesn't quite fit either. The universe isn't floating inside something larger. It doesn't have an outside because it contains everything, all of space, time, matter, and energy. Whether it's infinite or loops around on itself, it's self-contained. There's nowhere to step outside to. Even our sense of direction loses meaning on the scale of the universe. On Earth, we can point north, south, east, or west, but those directions depend on Earth's shape. In space, there is no universal up or down. Everything depends on where you are and how you're moving. So asking which way is the edge isn't really a simple question. This might all sound confusing, but it's also what makes studying the universe so exciting. We're trying to understand something far beyond anything we've ever experienced. The deeper we look into space, the more we realize that our everyday ideas of distance, direction, and boundaries don't work the same way on the cosmic scale. Space is not a flat, quiet emptiness. It stretches, it curves, and it may continue forever. Or it might fold back on itself in ways we haven't yet discovered. We still don't know the full truth, but that very mystery, that sense of standing on the edge of the unknown, is what keeps astronomers and physicists searching the skies, eager to find out what truly lies beyond the horizon of the observable universe. When we aim a telescope toward the vastness of space, we're not just looking at faraway places, we're also looking back through time itself. This happens because light does not travel instantly. It moves incredibly fast, at just under 300,000 kilometers per second. But even that amazing speed takes time to cross the enormous distances of the universe. So when we look at a galaxy that is 1 billion light years away, we're not seeing it as it exists today. We're seeing it as it was 1 billion years ago when that light first began its long journey toward us. In a way, every glance into the night sky is like opening a cosmic history book, written not in words, but in light. Because of this, there is a limit to how far into space, and therefore how far back in time, we can see. This limit is known as the particle horizon, an invisible boundary that forms the outer edge of what scientists call the observable universe. It acts like a giant transparent bubble surrounding us in every direction, showing us the farthest distances from which light has had time to reach Earth since the beginning of the universe. However, this boundary is not about 13.8 billion light years away, as one might expect from the age of the universe. It is much farther. This is because space itself has been stretching since the moment of the Big Bang. As light from distant galaxies travelled toward us, the very fabric of space was expanding, increasing the distance between us and those galaxies. By the time that ancient light finally reached Earth, those galaxies had moved much farther away than they were when their light first started its journey. Because of this continuous expansion, scientists estimate that the edge of the observable universe, our particle horizon, lies about 46 billion light-years away in every direction. That means the entire visible part of the cosmos forms a sphere roughly 93 billion light-years across. Everything within this enormous bubble is part of what we can observe. Beyond it, the universe might continue endlessly, but it is forever hidden from our sight. This horizon does not mark the end of existence, only the limit of visibility. Within this boundary, astronomers can study galaxies, stars, and vast clouds of glowing gas. They can trace the grand structure of space itself and observe how matter is spread out across the cosmic web. By studying the light that has travelled for billions of years, scientists can look back almost to the beginning of time and see the faint afterglow of creation, the cosmic microwave background, or CMB. This soft, ancient glow comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and for light to travel freely through space for the first time. That light has been moving ever since, filling the universe like a gentle whisper from its earliest moments. Today, with highly sensitive instruments, we can still detect it, a direct message from the dawn of everything. But beyond the particle horizon, everything becomes invisible. There could be galaxies out there just like our own Milky Way, filled with stars, planets, and maybe even life. Or they could be entirely different, shaped by conditions we cannot yet imagine. Yet if they lie beyond that horizon, their light will never reach us, and we will never know they exist. What makes this even more fascinating is that the horizon itself is not fixed. It changes over time. As the years pass, light from more distant regions of space finally reaches us, and our observable universe slowly grows larger. A galaxy that was once beyond our view might one day become visible. However, there is a catch. The universe is not only expanding, it is expanding faster and faster. This accelerating growth means that distant galaxies are being carried away from us at increasing speeds, with many now moving away faster than light itself. Because of this, another boundary appears, known as the cosmic event horizon. This horizon marks the ultimate limit of influence, a distance beyond which no event can ever affect us, no matter how long we wait. Light from anything beyond that invisible wall will never reach us, not even in the far future, because the expansion of space will always carry those distant objects away faster than light can catch up. It is a true one-way boundary. Once something passes beyond it, it is lost forever, not just unseen, but unreachable, cut off from our corner of the cosmos for all time. So while the particle horizon shows how far we can see right now, the cosmic event horizon shows how far we can ever hope to see, even with unlimited patience and the most powerful telescopes imaginable. Together, these horizons define the limits of human observation and understanding. They remind us that the universe we can study is only a small part of a much greater whole, a reality far vaster than we can ever directly experience. It is a humbling thought. We long to understand the entire universe, its full size, its shape, its beginning, and its possible end. Yet the speed of light and the finite age of the cosmos draw unbreakable boundaries around what we can know. No telescope can look beyond them, and no spacecraft can ever travel that far. Still, science does not stop at the edge of sight. Astronomers use what they can observe to make educated guesses about what lies beyond. If the universe appears similar in every direction, and if the same physical laws apply everywhere, then perhaps the unseen parts of the universe resemble what we can already see within our horizon. This assumption, that the universe is roughly uniform on large scales, forms one of the foundations of modern cosmology. Yet it remains an assumption, one we cannot test directly. We may never know how large the entire universe truly is, or whether it has any edge at all. But within the boundaries set by light and time, we continue to explore, discover, and learn. Every new observation, every faint galaxy detected adds another piece to our cosmic map. A map that will always be incomplete, but one that still tells an extraordinary story of where we are in the grand expanse of existence. We often hear people say that nothing in the universe can move faster than light. That's true, but only when we're talking about things moving through space. The expansion of the universe is something completely different. It's not about stars or galaxies flying through space at incredible speeds. It's about space itself stretching and growing. And that stretching has no speed limit. Imagine a rubber band with tiny dots drawn on it. When you pull the rubber band, the dots move apart, not because they're sliding across the surface, but because the rubber itself is expanding. The same thing happens in our universe. The farther away a galaxy is from us, the faster it seems to be moving away. This relationship is described by something called Hubble's law, named after the American astronomer Edwin Hubble, who discovered it in the year 1929. Hubble's law says that if you double the distance to a galaxy, you also double its speed of recession. There comes a point, however, where this apparent speed becomes greater than the speed of light. They speak of vacuum fluctuations, tiny tremors in the emptiness of space that might have given birth to our universe. Some suggest that our universe is just one bubble among countless others in a vast multiverse, each following its own set of physical laws. In these models, perhaps our universe simply formed by chance, emerging from a sea of endless possibilities like a single wave on an infinite ocean. These ideas are fascinating, filled with mathematical beauty and daring imagination. Yet, even with all their detail, they don't always quiet the deeper questions. Because if our universe came from something else, from a larger field, a deeper rule, or an unknown dimension, then we can still ask, where did that come from? What made it possible? Who or what built the foundation of all foundations? When we think of the universe as something that has limits, we are forced to imagine something outside those limits, something that is not the universe. For some people, that something else is God, or a creative force that exists beyond space and time, the author of the Cosmic Blueprint. For others, the idea of an edge is only a sign of how limited human understanding still is. Maybe we're trying to stretch our minds too far, asking questions that make no sense beyond our own system, like asking, what is north of the North Pole? But even that famous comparison doesn't solve everything. After all, the North Pole still belongs to Earth. It exists on something. If the universe truly contains everything that exists, and if it somehow has an edge, then what lies beyond that edge cannot belong to everything. It must be something different, something beyond all we know, and that's what makes the question impossible to ignore. Some scientists insist that asking what lies beyond the universe is meaningless. They argue that the universe is not in anything, it is everything. There is no outside to ask about. But others are not convinced. They believe curiosity doesn't stop at boundaries, it crosses them. If we ever reached a cosmic edge, they say, we would have every right to wonder what lies beyond it, and whether the laws we know, space, time, energy, are the only ones that exist. Perhaps what lies beyond isn't nothing at all, but a hidden level of reality, invisible to our senses and instruments. Some thinkers even compare this idea to ancient philosophies and spiritual traditions that spoke of worlds beyond worlds, higher realms, layers of being, or a vast intelligence that shapes everything behind the scenes. These aren't ideas that can be tested in a laboratory or proven with a particle accelerator, yet they continue to inspire scientists and philosophers alike. They remind us that the universe is not just a puzzle to solve, but a mystery to experience. If the universe truly has a boundary, then it challenges our most basic ideas of existence. We are used to thinking that everything has a cause and a limit, but if space and time themselves had a beginning, and perhaps even an end, then our ordinary tools for asking why might no longer work. We might be facing questions that language itself cannot express. Still, it's almost impossible not to wonder. If there really is a final wall somewhere in the farthest reaches of existence, did someone, or something, place it there? If the universe is a kind of structure, is it like a painting with a hidden canvas behind the colours? Is it like a vast building with unseen walls and an invisible foundation? And if so, who designed it? Who imagined it into being? These are not questions with simple answers. They cannot be tested or calculated. Yet they guide us toward the edge of thought, that quiet place where science meets philosophy and reason meets wonder. For all its power and precision, science is still part of a larger human story. A story driven by curiosity, by fear of the unknown, and by the unending desire to understand where we came from and why we are here. At the farthest edge of the universe, beyond the stars and galaxies, what we're really searching for may not just be the origin of matter or energy, but the meaning of existence itself. The holographic principle is one of the strangest and most fascinating ideas in modern physics. It suggests that the three-dimensional world we see all around us, full of people, mountains, stars and galaxies, might not be what it seems. According to this idea, everything that feels solid and real could actually be a kind of illusion, a projection from somewhere else. In simpler words, the universe might work like a giant hologram, a flat surface holding all the information needed to create the three-dimensional reality we experience. This isn't just a wild fantasy. It is a serious scientific idea that some of the world's greatest physicists have been studying for decades. The story begins with a mystery about black holes, those mysterious invisible objects in space where gravity is so strong that not even light can escape. When scientists studied what happens to information that falls into a black hole, they ran into a major puzzle. According to one view, the information should disappear forever once it crosses the black hole's event horizon, the invisible boundary that marks the point of no return. But that idea clashes with one of the most basic laws of physics: information can never be completely destroyed. The mystery deepened when physicists realized something strange. The amount of information that could fit inside a black hole didn't depend on its volume but on the area of its surface. Normally you'd expect that if you double the size of a box, it can hold 8 times as much stuff inside, because volume increases faster than surface area. But in the case of a black hole, the amount of information, the bits that describe everything inside it, seems to be stored on the outer surface, the event horizon itself. It's as if everything happening inside the black hole is somehow written on its skin. This strange discovery led scientists to ask a daring question. If black holes work like this, could the same be true for the entire universe? Could it be that all the information that makes up everything we see, every planet, every atom, even our thoughts, is actually stored on a distant 2-dimensional surface, like the film of a hologram, while our familiar 3-dimensional world is just a projection of that hidden reality? This is the heart of the holographic principle. It doesn't mean the universe is fake or that we are living inside a computer simulation. Instead, it means that the rules of the universe might be written in a lower dimensional form, the same way that a flat television screen can display a 3-dimensional movie. The screen itself is flat, but the picture looks deep and alive. From where we stand, the world feels completely real because we are inside the projection, unable to see the surface where the information truly exists, the source code of the cosmos. To get a sense of this, imagine holding a holographic sticker in your hand. When you shine light on it from the right angle, a 3-dimensional image appears, maybe a floating object or a figure with depth and shape. But the surface of the sticker is perfectly flat. The 3D image is created entirely by patterns printed on the surface. Now imagine that sticker is as big as the universe. The patterns at its edge, the boundary of space, might hold the true blueprint of reality. The world of length, width, and height that we walk through could simply be the grand projection of that deeper surface. You can also picture this using a balloon. The skin of the balloon is 2-dimensional, like a sheet, but all the air inside it fills a 3-dimensional space. Now imagine that all the information that defines everything inside the balloon, all the particles, forces, and even time itself, is written on the balloon's surface. The inner world we live in would then be a projection created by data encoded on the outer layer. In that sense, we would be living inside the image created by the cosmic balloon, never seeing the surface where the true information resides. In some versions of string theory, one of the leading attempts to explain the universe at its deepest level, the holographic principle appears naturally. These theories suggest that the complex universe we live in, with its stars, galaxies, and forces of nature, might actually be a shadow or reflection of simpler laws written in fewer dimensions. No one knows exactly where this lower dimensional space exists or what it looks like, but the equations seem to allow it, and they even help solve some of the most difficult problems in physics. One of those problems is how to combine the two great but very different theories of the universe: Einstein's theory of gravity, which explains large-scale things like stars and galaxies, and quantum mechanics, which governs the behavior of atoms and tiny particles. These two theories work beautifully on their own, but they don't fit neatly together. The holographic principle might be the missing bridge, showing that gravity in our 3-dimensional world could actually emerge from simpler interactions in a 2-dimensional space. If this idea is right, then space itself, the thing we think of as endless emptiness, might not be fundamental. It could be something that only appears when certain conditions are met, much like a shadow only appears when light hits an object. Even time might not be what it seems. It could be another part of the projection, something that emerges from deeper mathematical relationships. Of course, these ideas sound strange because they go against our everyday experience. We can touch things, walk through rooms, and move around freely. But nature doesn't always follow what feels natural to human senses. Quantum physics already taught us that reality is far stranger than intuition suggests. There's also another fascinating thought that comes from the holographic idea. If everything in the universe is encoded on a distant surface, then that surface might hold the entire story of existence, every galaxy, every particle, and every event that has ever happened. It could even contain information about things we can never see, like the hidden parts of the universe beyond the reach of our telescopes, or the mysterious dark matter that makes up most of the cosmos. Some thinkers even suggest that our thoughts, memories, and experiences might somehow be connected to patterns written on that boundary. In a poetic sense, it means the universe might have a kind of memory, a grand record written on its outer skin. Some physicists believe that one day we might be able to test this idea. They look to black holes, where the mathematics of the holographic principle is strongest, hoping to find evidence that supports the theory. Others study how gravity behaves at extremely small scales, searching for hints that space and time are not continuous, but instead built from tiny information-based structures. For now, the holographic principle remains a theory, a bold and beautiful attempt to make sense of some of the greatest mysteries in the cosmos. If it turns out to be true, it would completely change our understanding of reality. It would mean that the solid, colourful, moving world we live in is just one layer of a much deeper and more mysterious universe. Perhaps our entire existence, every star shining in the night sky, every breath, every heartbeat, could be like an image projected on the screen of space. And like a hologram, every small part of that image might contain traces of the whole, connecting everything to everything else in ways we are only beginning to imagine. If scientists ever found real evidence of an edge to the universe, a true cosmic boundary where space itself stops, it would be one of the most astonishing discoveries in all of human history. Not just for physics or astronomy, but for every branch of knowledge, because it would mean we had finally found the surface of the great hologram that creates our reality, the hidden canvas on which the universe itself is written. For thousands upon thousands of years, people have gazed up at the sky and wondered how far it goes. They have asked whether the universe has a shape, a centre, or a final edge where everything simply stops. These questions have haunted human curiosity since the earliest days of thought. Yet, in all that time, no one has found clear proof of a boundary. If, one day, we were to discover that such a limit truly exists, if there were a definite edge beyond which there is nothing at all, it would change nearly everything we think we know. Almost every field of science would need to be re-examined from the ground up. The first to feel the tremors of such a discovery would be cosmology, the branch of science that studies the origin, structure, and evolution of the universe itself. Right now, cosmologists generally agree that the universe has no edge. It stretches in all directions without borders, curving and expanding endlessly. But imagine if this picture were proven wrong. If instruments one day detected a true boundary, a place where space simply ends, it would upend every model and theory we have built for over a century. We would have to rethink how the universe was born, what it is made of, and how it behaves on the largest possible scales. Much of modern cosmology rests on an important idea called isotropy, which means that the universe looks roughly the same no matter where you look. If an edge exists, that balance would be broken. Space would no longer be equal in every direction. There would be a side of the universe that points toward the boundary and another that points away from it. That might sound like a small detail, but it would change everything, from how galaxies form and spread out to how light and energy move across the cosmic sea. We would have to rewrite the equations that describe the expansion of the universe, the way time flows, how galaxies drift apart, and how energy thins out would all have to be recalculated. Every bit of mathematics that describes the great cosmic story would need to be adjusted to include this new, unimaginable frontier. Physics as a whole would tremble under the weight of this discovery. For more than 100 years, our understanding of the universe has rested on two mighty pillars: Einstein's general relativity and the strange rules of quantum mechanics. Both of these theories assume that space-time, the fabric of the universe, is smooth and continuous. They do not allow for walls or sudden endings. If a real edge exists, then near that limit the laws of physics themselves might behave differently. The rules we rely on to build rockets, satellites, and particle accelerators might only tell part of the story. Scientists would then have to dig even deeper, searching for new principles that work not just here, in our familiar corner of space, but even at the edge of everything. Some would begin to ask whether the boundary is something physical or something more abstract. Is it a solid, impenetrable surface, like the skin of a sphere? Or is it the limit of space itself, a region beyond which distance and dimension lose meaning? If it is the latter, then new and unsettling questions would arise. What happens to energy when it reaches this limit? Does light bounce off it, or does it fade into nothing? Can particles strike this edge and rebound, or do they simply cease to exist? Do waves reflect, scatter, or vanish completely? These are questions no scientist has ever had reason to ask, because we have always assumed that space goes on forever. But if the universe truly ends somewhere, we would have to invent an entirely new physics to understand how reality behaves at its border. Astronomy too would enter a new era. Until now, every telescope, every space observatory, and every deep sky survey has been aimed outward, to look farther and farther into the darkness. Astronomers have mapped galaxies billions of light years away, traced faint glows left over from the birth of the cosmos, and searched for planets around distant stars. But if we learned that there is an actual outer wall where space itself stops, our attention would immediately turn toward that ultimate horizon. We would want to know everything about it, how far away it lies, what it looks like, and whether it could ever be reached. Missions that once aimed to explore other planets might instead be designed to find and study that cosmic edge. Entire space agencies could shift their focus from exploring the solar system to understanding the limits of existence itself. New kinds of instruments might be built just to peer toward that strange border. Telescopes that measure how light bends or fades as it nears the end of space. And then deeper questions would begin to stir. If there is a boundary in space, might there also be one in time? For ages we have believed that time flows steadily forward, without limit. But if space can end, could time also have a final moment? Would time itself come to a halt at the edge, or would it continue beyond, into something we cannot yet imagine? These mysteries would push both physicists and philosophers into realms of thought that have never before been explored. They would have to rethink what time means, and whether it is truly endless, or only a part of a larger finite structure. Mathematics, too, would face a profound challenge. For centuries, math has been treated as universal and eternal, an unchanging language of truth. But much of mathematics assumes infinite space or smooth, unbroken continuity. Calculus depends on the idea of endless division. Geometry describes continuous shapes. Algebra often stretches into infinity. A universe with an edge would break these assumptions. To describe such a cosmos, mathematicians might need to invent new forms of calculation, ones that deal with sharp discontinuities, sudden boundaries, and strange geometries unlike anything known before. Entire new branches of logic could grow from the need to describe a universe that ends. Naturally, the discovery of a cosmic boundary would also ignite fierce debate about what lies beyond it. Is there truly nothing? No matter, no light, no dimension, not even space or time? Or could it be the surface of a much larger reality, one that surrounds our universe the way an ocean surrounds an island? Theories from string physics and quantum gravity might suddenly become central. Some scientists already imagine that our universe could be a bubble floating within a greater, higher dimensional space. If the edge were real, those ideas might transform from speculation into serious science. We might begin to think of our universe as just one region inside a vast multiverse, like a single bubble in a boundless foam. Yet, beyond the science, there is something even more ancient in these questions. The idea of a cosmic boundary touches the oldest emotions and mysteries of humankind. What is the true nature of reality? What lies beyond the known world? Are there places we were never meant to see? Once such questions belonged to religion, poetry, and myth. But if scientists were suddenly faced with real evidence of an edge, those timeless questions would enter the realm of laboratories and telescopes. Physicists might one day write research papers on the nature of nothingness, or hold conferences on what beyond truly means. And the human response would be powerful and varied. Artists would paint the edge of creation. Writers would imagine journeys to the wall of the cosmos. Philosophers would ponder whether a finite universe limits our freedom or gives it meaning. Some people might feel trapped inside a cosmic container, while others might feel safer knowing that there is a boundary to all things. The discovery would also awaken one more unsettling question. If there is an edge, was it placed there on purpose? Could the universe itself have been designed, its borders drawn by some higher intelligence or hidden mechanism? Such thoughts might revive ancient debates about creation, destiny, and even simulation. The idea that the universe might be something crafted, like a grand program with coded limits. Whatever the truth, the moment we discovered a boundary to existence, humanity would never look at the night sky the same way again. The stars would no longer seem to stretch endlessly into forever. Instead, they would hang inside a vast but finite chamber, a cosmic dome filled with light and wonder, but also with mystery. And in that discovery, both humbling and electrifying, we would once again be reminded that even after all these thousands of years, we are still only beginning to understand where we truly are. Imagine for a moment that science, which usually tries to stay away from any ideas without solid proof, suddenly came face to face with something undeniable, a true edge to the universe. Such a discovery would shake the very foundation of human knowledge. Even the most skeptical scientists, those who never think in terms of meaning, purpose, or grand design, would have to pause. They would have to admit that the universe might be far more organized, far more deliberate than anyone ever dared to believe. The discovery of a boundary would not be just another scientific detail. It would force every classroom, every textbook, and every university course to change. The story of the universe, the one that told us of endless expansion, infinite distances, and eternal emptiness, would need to be rewritten. Generations of students who once imagined the cosmos as limitless would now learn that it might have an end, a frame, or perhaps even a visible surface. They would grow up in a world where the universe wasn't a vast ocean stretching forever, but a grand bubble with shores we might one day reach. And if that edge could be reached, if it was not just an abstract idea but a real, physical place, our curiosity would not let it rest. Humanity would surely try to send probes, spacecraft, or even light signals toward it. Could we use it as an observatory to look beyond, to study what lies outside our cosmic walls? Could that strange line mark the border between our universe and others, realms governed by entirely different laws of physics? The edge of everything could become the most studied region in all of science, the new frontier where the greatest mysteries wait. Every principle we hold dear, motion, light, gravity, time, and even logic itself, would be touched by the discovery. It would not just reshape cosmology, it would reshape what it means to exist. But then comes a question that feels almost too strange to ask. What if this edge isn't a physical border at all? What if it's something else entirely? A boundary not of space, but of simulation? Could we be staring at the limits of a vast cosmic program? As technology advances, we humans have become creators of our own miniature worlds. In modern video games and virtual realities, players wander through landscapes that feel alive, forests that whisper with wind, oceans that shimmer in sunlight, cities that never existed. Yet behind those scenes, computers are only showing what they must. They don't build the entire world at once. They generate details only where the player looks. It's efficient, smart, and necessary. And this idea leads to a chilling thought. If we can do this, might someone far beyond our understanding have done the same, on a universal scale? The simulation hypothesis asks this very question. What if our universe is not the ultimate reality, but something created by a civilization far older and more advanced than our own? The thought feels unsettling, yet strangely logical. After all, the universe seems almost too perfect for life. The laws of physics work flawlessly. The constants of nature fit together like pieces of an elegant equation, and the balance that allows stars, planets, and life itself to exist is breathtakingly precise. Why is everything so neatly ordered, from the spiraling arms of galaxies to the delicate structure of atoms? If someone were designing a reality, these are exactly the patterns we would expect. Clear rules, stable systems, and boundaries that stay just out of reach. When we design simulations, we do the same. We build worlds that appear continuous, but only render the details that are necessary. Perhaps the universe does this too. Some physicists have noticed that quantum particles behave strangely when observed, as if observation itself changes reality. Could this be a clue? In a simulated universe, the system might generate detail only when someone looks closely, just as a game loads a level only when the player walks into it. This idea blurs the line between science and philosophy. If reality depends on observation, could that mean the universe is running on code? A grand algorithm that decides when and how to show us the world? Even the constants of nature, numbers like pi, the speed of light, or Planck's constant might be hints. These values don't just work, they fit together with uncanny precision, as though written by the same hand. In a real simulation, such constants would be part of the software, unchangeable settings that determine how everything behaves. And just like any computer program, even the most advanced simulation would have its limits. There would be a maximum level of detail it could handle. If reality seems slightly blurry at unimaginably tiny scales, or behaves oddly under extreme conditions, that might be a sign of those hidden limits. Some researchers have even wondered if tiny irregularities in particle experiments or faint patterns in cosmic rays could be fingerprints of the underlying code, evidence that our universe is in some sense being computed. But if this wild idea were true, if we really were living inside a cosmic simulation, what would it mean for us? Would it change anything about love, loss, beauty, or hope? For many people it wouldn't. A tree still gives shade whether it's made of atoms or pixels. The warmth of sunlight feels no less real, whether it's produced by physics or programming. Whether our lives are chemical or coded, our feelings still matter. Reality, whatever it is, remains ours to live in. Yet for others, the implications are staggering. Who built the simulation, and why? Was it made as an experiment, a story, or a game? Could there be hidden messages within nature, tiny patterns or signals like secret comments in the code, left behind by the builders? Or perhaps the simulation was never meant to be discovered at all. Maybe we are like characters in a book, unaware of the author who writes our every page, unable to see the paper beneath our world. The simulation idea also changes how we think about time. In such a world, time might not flow in one direction. It could be paused, reversed, or even replayed without us ever knowing. If the system were reset, everything, stars, galaxies, even our memories, might simply adjust to the new version of reality. We could be living through cycles without noticing, our entire history written and rewritten like lines of code. And what lies beyond? If our universe is a simulation, is there a real universe outside it? A higher level of existence that built ours? Are we just one layer in a stack of countless worlds, each one simulating the next? It's a dizzying idea. Universes nested within universes, each one a reflection of the one above it. When we think about how fast human technology has advanced in just a few centuries, it doesn't seem impossible that somewhere, someone, long ago or far away, has gone even further. Still, for all its intrigue, the simulation hypothesis remains unproven. No one has found a line of cosmic code. No one has cracked through the invisible walls of our reality. For now, it's only a possibility, but one that changes how we look at everything. When we gaze into the night sky and see the faint glow of distant galaxies, we might be staring not only into space, but at the very edge of what we're meant to see. Perhaps that cosmic horizon, the farthest reach of light, isn't just the limit of the visible universe. Perhaps it's the end of the rendering, the outer boundary where the simulation stops producing more detail. Beyond that line, there may be nothing at all, not because the universe ends there, but because for now that's all the program allows. And if the universe is truly infinite, then perhaps there are infinite versions of you too, each one walking through its own simulated world, unaware of the layers above or below. Whether or not that's true, the mystery remains. We may never know if we are players, characters, or creators. But in asking the question, we do what we've always done best, reach toward the edge of understanding, eager to see what lies beyond. In the part of the universe we can see, matter is not just scattered randomly. It is organized, woven into vast structures. Galaxies cluster together, forming immense cosmic neighborhoods. Within one of those galaxies, a star shines like our sun, and around that star orbits a small blue-green planet called Earth. On this planet, life emerges. Tiny at first, barely noticeable, but over billions of years, that life grows more and more complex. It learns, adapts, and eventually creates wonders. It builds tools that extend its reach, composes music that moves the soul, writes stories that capture imagination, and even launches rockets that pierce the skies, reaching toward the stars themselves. Every single event in this grand story, from the swirl of particles that shaped your fingerprints to the exact shade of paint on your childhood bedroom wall, depends on how matter was originally arranged at the beginning of everything. But there is a limit. Even though the number of ways particles can arrange themselves is unimaginably vast, it is still a finite number. And when we compare that number to the idea of infinite space, it suddenly becomes almost trivial. If space stretches on forever, endlessly in every direction, then every possible arrangement of matter is bound to occur. Not just similar arrangements, not just echoes or close imitations, but exact repetitions. Somewhere, far beyond the limits of what we can see or travel to, there exists a patch of space, a tiny bubble that is identical to the part of the universe we inhabit. Within that bubble is a galaxy like the Milky Way, a star like the Sun, a planet like Earth, and on that planet, a version of you. This other you is unaware that they are a copy. To them, they are the original. They live, laugh, cry, and wonder, thinking their experiences are unique, just as you do. And even farther out, there is another version of you, slightly different because of a single choice made differently. Perhaps they turned left instead of right on a fateful day, or chose not to return a phone call. That tiny change sends their life down an entirely different path. Even farther still, another version of you exists, perhaps living as a pilot, a poet, or in a city you have never seen. If space is truly infinite, and the laws of physics are consistent everywhere, this repetition is not just likely, it is inevitable. Of course, these duplicates are unimaginably distant. They are not hiding behind the moon or orbiting the next nearest star. The distances are so vast that they challenge our understanding of numbers. Some estimates suggest the closest exact copy could be 10 to the power of 28 meters away. That is, a 1 followed by 28 zeros, a number so colossal, so incomprehensible, that we lack a name for it. Even if these copies exist, we would never meet them. We would never even know they are there. Yet just knowing they might exist reshapes the way we see ourselves and our place in the cosmos. If infinite versions of you exist, what does that say about identity? Are you truly unique? Does your life still hold meaning? Some people take comfort in the thought, imagining that somewhere, some version of themselves is living the life they always dreamed of. Others find it deeply unsettling, like being trapped in a cosmic hall of mirrors that stretches on forever. Scientists sometimes call this idea the Level 1 multiverse. It is a vision of an infinite universe with endlessly repeating regions. This is very different from other multiverse theories that imagine completely separate universes with different laws of physics. The Level 1 multiverse does not require hidden dimensions or mysterious portals. All it needs is endless space and the same physical rules we observe here. That is enough for repetition to emerge naturally. Even in a universe where repetition occurs, most of space could still be empty, dark, and cold. These repeating regions are so staggeringly distant that for all practical purposes we remain utterly alone. Each copy of you is isolated by inconceivable distances and unimaginable spans of time. From a mathematical standpoint, however, they exist, echoing your own existence. We must also be careful with the idea of a copy. Physics does not care about names or faces. It cares about how particles are arranged and how energy flows. If two systems have the same arrangement of particles, they are considered the same, even if their memories are different or stored in a slightly different way. If every neuron in your brain is arranged identically and fires in the same pattern, that copy would think it is you, feel it is you, and live its life believing it is the original. Perhaps our universe is not special, not central, not the first, not the most important. Perhaps it is just one tiny tile in an immense, endless mosaic of reality, no more real than any other. And if this is true, then the concept of reality itself may be far more fluid than we imagine. In a universe of infinite possibilities, every choice, every moment, every version of reality exists somewhere. What we call normal or rare may simply be an illusion, a matter of perspective. Could we ever prove this? At present, these ideas come from theory, from mathematics and logic, from the careful stretching of imagination along the edges of what we can test. In these moments, science begins to feel very much like philosophy. Still, the idea cannot be easily dismissed, for it may be the natural conclusion of what we already know. Space is expanding, the observable universe is only a small patch, and the same physical laws seem to operate everywhere. If this pattern holds, then somewhere right now, a version of you is listening to these very words in a room much like yours, asking the same questions, wondering, just as you do, am I alone? This brings us to entropy and the fate of the universe. In everyday life, we see things wear down. Ice melts, fires burn out, batteries lose their charge. This is entropy, the tendency for energy to spread out, for order to break down, for systems to move from useful energy toward disorder. Hot things cool, engines wear out, living beings die. Entropy is a law of nature, not a suggestion. And it is not limited to small systems. It applies to the universe as a whole. The concept of heat death arises from this. If everything tends toward disorder, then the universe itself will gradually approach a state where all structure, all motion, and all energy differences vanish. Stars will burn out, galaxies will darken, even black holes will slowly evaporate. All that will remain is a thin, cold mist of particles, evenly spread, without light, without energy to drive change. This is thermal equilibrium, a universe that is the same everywhere, utterly still, utterly unchanging. But what if the universe is infinite? Can a limitless universe ever truly run down? Entropy, as we understand it, still applies locally. It governs star systems, galaxies, even patches of space the size of small rooms. Heat spreads, energy evens out. But in infinite space, there is always more room for new structures to emerge. One part of the universe may be dark and dead, while a distant region still sparkles with newly forming stars. Every region has its own timeline, its own pace. Yet, if entropy keeps rising everywhere, eventually every region reaches a state of maximum disorder. The only way to avoid heat death is some cosmic mechanism that resets order, bringing back patches of low entropy. On Earth, sunlight allows plants to convert energy into structured molecules, temporarily reversing local disorder. In the universe, ideas have been proposed that black holes, as they evaporate, might seed new regions of space with fresh low-entropy conditions. Quantum effects might allow tiny pockets of order to arise from the chaos. These patches could, in theory, grow into entirely new universes, starting the cycle anew. Even so, each universe, even each newly sprouted one, eventually faces its own heat death. And in a universe infinite in both space and time, entropy seems to demand that all energy will eventually be used up. Yet some thinkers speculate that, by sheer chance, order could spontaneously arise from chaos. If particles randomly settle into just the right patterns, a new star or even a new universe might form. These are called fluctuations, but the odds of such a fluctuation are so astronomically low that it would take far longer than the 13,800,000,000 years that our universe has existed. And here, the story of the cosmos becomes stranger still. In infinite space and endless time, every possible reality might already exist, every possible variation of you already lives somewhere, and every universe, no matter how temporary, leaves a trail of potential echoes stretching into eternity. What seems impossible, improbable, or miraculous is simply inevitable when infinity is involved. The cosmos, in its vastness, becomes a place where imagination, mathematics, and reality dance together, revealing a universe far more wondrous, strange, and beautiful than we ever dared to dream. Some scientists suggest that if the universe goes on forever, small random events are much more likely than large ones. This means that if order ever returns in the vast emptiness of space, it might not come in the form of a whole galaxy or a planet. Instead, it could appear as something tiny, like a single brain, popping into existence for a brief moment, carrying memories of a life it never actually lived. This strange idea is called the Boltzmann brain scenario. It sounds unsettling, but it highlights how deeply the concept of entropy, how disorder spreads, affects our understanding of time, space, and even our sense of self. A central question is whether entropy has a final limit. Is there a point where the universe reaches its maximum disorder, where nothing new can happen? Or can the universe always become more chaotic, more spread out, and more uniform? If space and time truly stretch on forever, then perhaps entropy does too. If that is the case, the universe would never have a final ending. It would simply continue changing, growing flatter, colder, and quieter with every passing moment. This is why the idea of heat death, the universe slowly fading away, feels so vague and mysterious. Here in the part of the universe we can observe, we can predict how stars will burn out and how galaxies will fade over billions of years, but we cannot yet see the full picture. There could be regions where new energy is still being formed, There might be structures or cycles in the fabric of space that slow down entropy or even reverse it. Or perhaps entropy is the deepest law of all, unavoidable even across infinite space and time. The difficulty is that our tools and theories are made for what we can actually observe. We understand how entropy works in laboratories, in engines, and even in living cells. We have modelled its effects in stars and galaxies. But beyond the observable universe, we are left with only mathematics and logic. And while math can take us far, it has its limits when we venture into the unknown. Maybe the heat death of the universe will not be a sudden, clear end, but a slow fading, a gentle quieting without a sharp conclusion. Perhaps it is like a song that grows quieter and quieter until it becomes a mere whisper across an empty field. Or maybe it is more like a tide, rising and falling across distant regions of space and time, sometimes bringing order, sometimes bringing disorder. Thinking about the end of the universe naturally leads to deeper questions. Does the end of all things also mean the end of meaning? When we imagine the universe dying, we often picture cold, dark, still emptiness, and it feels final. If everything ceases to exist, does that include meaning itself? Telescopes and equations can predict the fate of matter and energy, but they cannot tell us how to feel about it. If all that exists is moving towards stillness, collapse, or disappearance, what does that say about us, our lives, our choices, our awareness? Humans have wondered about the meaning of life for as long as there have been humans. But when we place that question against the scale of the universe, with its vast size, its incredible age, and its possible endings, it begins to feel different. The universe does not seem to care about our concerns. It merely expands, shifts, and evolves, according to laws we are still trying to understand. In that vast silence, it is tempting to wonder if meaning is simply something we invented to fill the emptiness between the stars. For some, the realization that everything must eventually end makes life feel fragile or even pointless. Why strive? Why love? Why create if all will vanish? A person might live a meaningful life, only to die. A civilization might flourish, only to crumble. A planet may thrive for millions of years, only for its star to burn out. Even if we could somehow extend life, survive through machines or colonize other galaxies, the same cosmic rules would catch up. Energy continues to disperse, entropy continues to grow, the ending still approaches. Yet for others, the same truth inspires a very different response. If everything is temporary, each moment becomes more precious, not less. Meaning is not erased by the inevitability of endings, it is created by what happens before they arrive. A sunset is beautiful not because it lasts forever, but because it ends. A song concludes, yet it can still touch our hearts. A life may be brief compared to the life of a star, but that brevity does not make it empty. It makes it rare, unique, and remarkable. Many philosophers have argued that meaning is something humans bring into the world rather than something we find waiting for us. The universe may remain silent, but we speak into it. We think, we create, we imagine, we suffer, and we care. In doing so, we make something real from something that is otherwise silent. We are the makers of meaning. Still, the concept of an ending can cast a long shadow, especially when imagined on a cosmic scale. Heat death, where all energy is evenly spread and nothing changes. A big rip, where space itself tears apart. Or a collapse back into a single point, erasing time. All are endings that are more than physical. They carry emotional weight. They suggest a kind of silence deeper than death, a stillness that seems impossible for thought to survive. But does such cosmic silence erase what came before? Many would say no. Even if the universe forgets us, our presence remains real. Our thoughts, struggles, hopes, and joys were real. They mattered, if only to us, and perhaps that is enough. Perhaps the meaning of life does not require eternity. Perhaps it is enough simply to exist, to be aware for a while in a universe that mostly is not. Some thinkers go further. If the universe ends, does that truly mean everything ends? Could there be something beyond, a greater reality we do not yet comprehend, where our actions and lives are preserved or remembered? We cannot prove it, but this is a hope that has comforted many, not just for themselves, but for all life. Religions across history have offered many versions of such ideas. Souls that live on, cycles of rebirth, eternal realms beyond space and time, unity and purpose built into the world itself. These beliefs do not always match what physics tells us, but they arise from the same human need, to know that what we are and what we feel matters in the long run. Physics itself sometimes hints at strange possibilities. Maybe new universes can form, maybe time can restart in another place. Perhaps information is never truly lost, only transformed. Some theories even suggest that what we see as the end might just be a transition, a doorway to a deeper level of reality. In such a case, the story of existence could continue, even if in forms we cannot yet imagine.